We're still missing one of the Flash Talk presenters, but we will start anyway. In 3 minutes or so, I'll give you a little bit of a heads up. You have each 7 minutes to present, with 3 minutes for questions and answers. I'll be giving you a non-audio clue to what's going on my screen 2 minutes before your time is up, and another 1 minute before your time is up. That will be audio. You both have co-host permissions, by the way, so you may share screen without a problem.
So can I try once that the screen share option is okay or not? Like I can share the screen or not?
Sure.
Give it a try.
Yes. Right? It's fine.
Yes, it's working. We can see. I don't see the presentation though. Maybe you shared only one screen.
No. No.
I'm just seeing the PowerPoint window. When you share the screen, you should press share the whole screen so that you won't have that problem.
But I did the slideshow from beginning.
Now it's working.
Working?
Now it's not.
No.
Paz, is it okay for you if we start with her since she's already sharing the screen?
Yeah, it's fine. No worries.
So try sharing your screen from the beginning. And this time, share the whole screen.
How to do that? From beginning slideshow.
The sharing is from
Stop
Zoom,
your
not
share.
from PowerPoint.
Stop the share screen and then share again. And this time, click on share whole screen.
Stop share. Stop share. No.
Share again.
Share screen. Now.
We're only seeing the folder that's open.
This one? No.
Did you open the presentation? Is it? Yes. Are you seeing it right now? Because we are seeing the folder. Maybe. Let's stop your share. I'll give Paz his opportunity to start and
Okay.
try and ask someone for help, or if not, I will try to assist you.
Okay, so you're seeing the slideshow, right? Am I okay?
You're okay.
Okay. So, hi everyone. My name is Paz. You want to start, Nitai, or can I start?
You can start because we're a bit 2 minutes late.
Okay, okay. Hi, my name is Paz. I'm currently at my PhD in Ben-Gurion University, but today I will present a work that I did in Ariel University during my master's. So it's about the synthesis and characterization of solid oxide fuel cell anode by inkjet printing process, and supervised by Dr. Konstantin Borodiansky and Professor Michael Zinograd. Okay. wait, sorry. Okay, so excuse me. So let's begin with the fuel cells. Fuel cells are devices which converts chemical energy of redox reactions into electricity by absorbing gas phase fuel and oxidant on the electrodes. By using hydrogen fuel in these devices, they produce clean energy with only water as the product. So solid oxide fuel cells are a category of high temperature fuel cells, which are made of solid ceramics components. These kind of cells are mainly designed for heat and power systems and processes. So in my work, the main motivation was to introduce a more simple and scalable technique to manufacture the anodes for the fuel cell. So my objective were to create high surface area anodes. So they need to be porous in microstructure. Also, they need to have good catalytic activity of hydrogen oxidation reaction, and is required. So I need to choose. So I chose as nickel and gadolinium doped ceria as the material of fabrication. Nickel is used as the electron conductive phase, and the gadolinium doped ceria is the ionic conductive phase. Both are critical for creating the triple phase boundaries, which are the active site for the anodic reaction. And for the method of fabrication, I chose to use the commercial inkjet printer because it's fast and simple to operate. Okay, so for the synthesis of the ink, I used nitrate salts for nickel, cerium, and gadolinium, and surface active agents to maintain uniform particle size over time. I chose ammonium carbonate as the precipitating agent and water as the solvent. After mixing all the components for 7 days in room temperature, the ink was ready to use. The fabrication process was to synthesize the ink, load it on a printer, and calcinate after each cycle. Afterwards, the sample was sintered in 1200 degrees Celsius to achieve the final product, which was the nickel GDC anode on the ceramic electrolyte. So if we go over the results and characterization, the synthesized ink had relative stable particle size over time, which means we can use it for long periods. The rheological properties of the ink are suitable for printing as synthesized, which means that the viscosity, density, and the surface tension of the liquid was suitable for this specific printer. The printed anode had a desired porous microstructure, as I said before, and the desired phase of nickel oxide and gadolinium doped ceria. By testing the anode performance in a fuel cell, it shows that there is a potential for further development in terms of maximum power density that we get. So in conclusion, my research introduces a fast and simple method to fabricate solid oxide fuel cells anode, which in par with other techniques in fabrication of synthesis, and the results show great potential for increasing cell performances, providing the further development and adjustment of the fabrication process. So thank you for listening.
Very nice. Thank you, Paz. It was an interesting talk, and it was right on time. You had even 1.5 minutes to spare, so very nice.
Okay.
If anyone from the audience would like to ask a question, go ahead. The floor is yours. If not, I would like to ask one question regarding the printing process itself. What is the printer's resolution and what's the smallest line width you can get to?
Well, I can't remember the specific details at the moment because it's been a while, but we're talking about you mean the drop sizes and the resolution of them?
Yes, yes.
Okay, so the drop size is supposed to be a few well, I'm sorry, I cannot remember, but I think the diameter of the drop size was like few micrometers, like 1 or 2.
Okay, so either way, it's definitely not a nano technique in any sort of way. It will be for micro
yeah.
fabrication.
Yeah, and I mean, what is supposed to be like if you want to make it better, like make the particles small, and of course it goes through long-term long time of sintering, so there is a growth, so you need to maintain it as small as possible, but and still maintain a power structure, which is very let's say challenging.
Okay, great. Thank you for your answer. Anyone else from the audience wants to ask anything? If not, then I'll thank you again. I enjoyed your talk and we'll move on. Asmita, are you fine now? Can you share the screen properly and everything?
Yeah.
Try pressing the presenting screen here where you are, yeah.
What?
Now it's fine.
I don't see the presentation itself.
Yeah,
yeah, it's not. I think that it's my turn, maybe. Then?
Yes, it was supposed to, but since you logged in now, we are starting with we're going on with who was here before, and we'll let you have your turn third.
Okay.
After Asmita. If you are not managing to share the screen, let's just use the slides themselves, and we'll be fine.
Is it visible now?
Is it visible?
We can only see the screen itself, the PowerPoint.
So, but slide by slide, I can say. I don't know why it is not sharing.
Just show it slide by slide. It should be fine.
Yeah. I
Is
think,
this visible?
yeah, the slides are there. I think
You
now
can see
you
the
can
slides
see.
themselves.
Yes, so slide by slide, I can. Yeah. Yes. Now I can. Right. Can I start now?
Yes, definitely. Start.
Yes. Hi everyone, my name is Ashmita Datta. I'm a PhD student of Arbell University working with carbon nanoparticles and its composite under the supervision of Dr. Arya Burenstein. Today, I like to present my work on laser carbonizations of carbon materials to prepare the flexible electronics. So first come the preparations of RGO-CNT composite. So basically composites are when two or more materials combined with not only mix, but also the well interaction result in the synergistic effect, which leads to produce the unique and superior behavior. CNT-based nanocomposite have received the huge attraction nowadays because of the alternative of the conventional composite due to its mechanical thermal, electrical properties, chemical properties, and tensile strength. So we choose GEO with the CNT to prepare a better composite. GEO in our lab, it is produced by the modified Hammers method, and the CNT is a rolled up sheet of sp2 hybridized carbon, and it doesn't have any effect on the laser carbonization. So we need to modify the CNT, one-step modification of the CNTs to build the carbonyl groups or the higher oxygenated groups on the surface of the CNTs. Next come the laser carbonizations of GeoCNT composite to form the RGO-CNTs. So I put one short video to understand how laser works. Here you can notice the color change from dark brown to black after the laser treatment. The advantage of the laser carbonizations over the conventional carbonization is that the laser carbonization takes only a few milliseconds, whereas the conventional carbonization takes hours. The structural analysis of the RGO-CNT composite is done by the Raman spectroscopy. Here you can see in the graph that the Raman spectroscopy of the GeoCNT composite and the GeoCNT composite after the laser conversion. The Raman techniques is very much useful to characterize the carbon materials after the laser treatment. As you can see in the graph, there is two kinds of peaks, and one is the D band and another one is the G peak. The D band appears at 1350 semi-inverse region and the G band appears at 1583 semi-inverse region. The D band originates due to the disorder orientations, and the G band occurs due to the stretching of the C-C bond inside the sp2 hybridized carbon. So you can see in the graph that the GeoCNT composite, the D band is larger as compared to the G band, but after the laser carbonization, for the RGO-CNT composite, G band become intensely strong, and another one, the two D bands appear at 2600 semi-inverse region, which is the characteristic peaks of the graphitic sp2 material. So we can confirm that the GeoCNT, the conversions of the GeoCNT to RGO-CNT, it's done to the GeoCNT and RGO-CNT. We can confirm by this study. We also did the same and same. So to understand the well interaction between RGO and CNT, here you can see the CNTs are attached on the surface of the graphene sheet. In same image also we can see the tubes are adhere on the surface of the graphene. So next come the applications of the RGO-CNT composite. We have the GeoCNT slurry. We can put it on the PET film, and after the laser carbonization, it's become the RGO-CNT. The characterizations of the electrode can be done in rest state and in bending inside and bending outside. So when it's bending inside, you can see the resistance increases and the conductivity decreases. But when it is relaxed, it's come to its rest positions. Whenever the electrodes are bending outside, the conductivity increases and the resistance decreases, as you can see in the picture, which is totally reversed when the electrodes are bending inside. So this incident we can explain by that the physical properties of the individual layers or the interface between layers may be improved during bending. During bending inside, when the electrodes are bending inside, the gaps between layers increases and the contacts, they loses the contacts. Whenever the electrodes are bending outside, gap decreases and they have a more contact. That's why the conductivity increases. So from the above study, we can conclude that the productions of the flexible electronics is possible On the PET film, the productions of flexible is possible in the PET film due to the productions of the conductive carbon network, and we can also generate the low-cost, thin, and unbreakable electrode for the higher performance devices. The supercapacitor application is also under investigation. So at last, I would like to thank my beloved lab members for helping me, and Dr. Arya Borenstein for his constant support. Thank you. Thank you so much.
Thank you very much, Asmita, for your interesting talk. Are there any questions from the audience? If not, I would like to clarify maybe something that I could have missed a bit about the Raman spectra you showed before.
Raman?
Yes.
Yes. Yes.
Can you explain a bit more about the chemical between the two spectra?
Yes. So the blue curve, it's the geo for the composite, that you can see the D band is larger and the G band is shorter. But after the laser treatment that I showed in this slide, that the laser changes the material. After the laser treatment, it's produced more like graphene structure. It becomes graphene that we denote as the RGO CMT. Means RGO means reduced graphene oxide. The reduced graphene oxide, it's graphene. So it is a characteristics peaks like this G peak is a characteristics peak for the graphitic material, and it is the second order vibration of the G peak, the 2D band. For this material, it doesn't have this 2D peak. The 2D peak is only appear for the graphitic material, graphitic sp2 material. The G band, it's the G band, and these 2D bands, it's the characteristics peak, kind of signature peak for the graphitic material. So we convert the GeoCNT composite to RGO-CNT composite after the laser treatment. So it is before and after the laser treatment, these two graphs, the same material, but the before, this one is before the laser treatment and the red one is after the laser treatment.
Great, that really answered my question well. Thank you very much. We're out of time, so we'll move on to Chen now. Thank you very much.
Thank you very much.
Sorry, I'm on mute. Now I'm okay. I will just share the screen.
Maybe, Asmita, you should first stop your share.
Yeah, I will stop sharing. Yes. Yes.
Okay, just a moment. Can you see my screen now?
Yes, it's working.
And do you maybe see the last sentence IVS? Okay.
It's also visible.
Okay. 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 So I will start. Hi, everyone. My name is Chen Oppenheim. I'm a master's student in Weizmann Institute in the group of Michal Eskes, and I'm investigating about the ceramic polymer interface in composite electrolyte by NMR spectroscopy. So nowadays in the industry, we use lithium-ion batteries, and how it works, we have electrons that come from the anode to the cathode in external way, and lithium-ion that go from the anode through the liquid electrolyte to the cathode. And in case of something, they return to the anode. So why we use liquid electrolyte? We use liquid electrolyte because it has high ionic conductivity. And we have problem with that. What is the problem? Is that we have low electrochemical stability window. So when lithium ion go to surface with high energy, they aggregate and then create a path that called dendrites. And eventually it can reach to the cathode. And because of the fact that liquid is flammable, we have the risk that the battery will explode. So we want to have a good battery, safe battery. So for that, we will change the liquid electrolyte to solid, that it's much more safe. So the main solid electrolyte is a composite of a polymer PEO that is to improve the flexibility of the battery, lithium TFSI salt that release free lithium ions and suppress the polymer crystallization, and inorganic ceramics that had high lithium ion conductivity at room temperature, and higher elastic modulus. And we use in our system LAGP because it's not hair sensitive, not toxic, and also high electrochemical stability window. The problem that we have with solid electrolyte that it has low ionic conductivity. And according to the literature, we have three options for path of lithium ion inside the composite. The first one is that the lithium ion go through the chain's polymer. The second is through the ceramics. And the third is that it goes in the interface between the polymer and the ceramics. And it's found out that the interface is the best path for lithium ion conductivity. So it's important to understand this interface, but the chemical nature and the reason for this higher conductivity remain unclear. So our approach is development of a solid-state nuclear magnetic resonance NMR technique that can selectively probe this interface. So NMR provides information about the composition, about the chemical nature and the mobility. And we can see here that the NMR signal intensity is proportional to the different population of the nucleus spins. And also this difference called nucleus polarization. But the problem that we have with NMR that it's limited in sensitivity because the polarization of the nucleus is low. So we're using electron spins to gain this sensitivity. The electrons has high polarization, as we can see here. And according to the irradiation of the microwave, we can transfer the polarization from the electrons to the nucleus. Usually people use radical solution, but the problem that we have is this, that it's really reactive. So we change the properties of the material. Our group is the first one to use paramagnetic metal ions for inorganic oxide materials, solid materials. And we use it for LAGP. We dope the LAGP with chromium, iron, and manganese that can replace the aluminum in the LAGP. And they have unpaired electrons that can transfer their polarization to the nucleus inside of the interface. So we synthesized the LAGP and we checked it in the LAGP, characterized this, and we can see that we have high weight percent. Also, we put dopants inside of the LAGP, we get still a high weight percent. In addition, we also did a composite, we synthesized the composite, and we checked it in the SEM, and we can see here the spread of the particles of LAGP, the white particles, that it's really homogeneously inside of the composite. Also really important to understand what is the lithium ion conductivity of this composite. So for that, we did experiment of the galvanostatic cycling of symmetric cell. This means that we have the composite and the electrodes, the anode and the cathode are from a lithium metal. So in this way, we're supposed to get a voltage that's equal to 0. But according to the resistance of the composite, we will get overpotential. So as long as the overpotential is lower and near to the 0, the higher the lithium ion conductivity. And we can see here that we get really good result, 0.57 of the overpotential. We also want to see to improve that we have the amperes inside of the LAGP. So we recorded electron paramagnetic resonance, as we can see here. And we see here in the line in black that this is represent the end of the LAGP, that we didn't get an EPR signal. But when we dope the LAGP with chromium, iron, and manganese, we will get this signal EPR, as we see here. And when we increasing the doping from 90 to 76, we increasing also the EPR signal. So we successfully improved that we have unpaired electrons inside of the LAGP. We have this paramagnetic metals ion inside of the LAGP. We wanted to use chromium and iron because it looks promising, but we found out that we cannot use it according. What? Sorry?
Just said that it's the final minute. Go on.
Okay, sorry. That we have only that we have difficult techniques, so we cannot use it, and we use the manganese. And when we did the NMR, we can see the spectrum of lithium 6 and 31 phosphorus isotope. And when we radiate the microwave to create this transfer polarization, we can see that we have enhancement of the signal of good factors, so we can use this manganese for our purpose. It's also important to see which one of the concentrates, the 19, the 38, or 76, is the best one to use for this enhancement. And we found out that the best one is 19 millimolar manganese. So to summarize, the composite tetrahydride that we are doing is really successful and has a lower over potential, and we can replace the aluminum by manganese inside of the LATP to provide high signal enhancement, especially 19 millimolar concentration. And the future plans is to addition of organic additive to lower more the over potential that we have, and also using the manganese to probe the interface and understand the effect of the additive. Thank you very much for your attention. Thank you for all the people that helped me, especially Michal Eskes, Bridget, and thank you very much for your attention. And if you have a question, please ask. I will be glad to answer and to discuss. Thank you.
Thank you very much, Chen. Interesting talk. Really, I'd like to see it. And if anyone has any questions, the floor is free.
Please ask us.
Well, if no one has any questions, and I have to say I can't really think of one, I would really like to thank you all again. And it was wonderful hearing your flash talks and hearing about your research. And we will meet again at the plenary session of Yuri Gogotsky.
Thank you very much. Bye-bye.
Thank you.